So now in this lecture we start the fluid mechanics, right? Fluid dynamics, right? The fluid dynamics. First, the types of fluid flow, right? Types of fluid flows, right? Types of fluid flow. The first is the steady flow, right? Steady and unsteady flow. Can you explain what is that? Yes, steady and unsteady flow. Suppose if the water is moving like this, it is flowing in this way. In the steady flow, listen one thing, in the steady flow, if the velocity of the particle or the particle is v1 at this point, when it reaches to other point, the velocity become v2. Is it clear or not? When this particle 1 reaches to the point 2, all right, the velocity of this particle again become v2. That is, if any particle is passing through this point, suppose this is the particle, any particle, when it reach to the point 1 and reach to the point 2, so when it reach to the point 1, its velocity v1, and when it reach to the point 2, the velocity is v2, right? In which the like velocity, pressure, density do not change with the time. Steady flow. What is the steady flow? I am writing velocity, pressure, and density at a point do not change. This is the steady flow. Are you getting or not? And in unsteady flow, what is the unsteady flow? The velocity, pressure, right, and density varies with time, right? So this is called the unsteady flow. All right. In steady flow, we are going to discuss only the steady flow, not the unsteady flow. In this steady flow, the streamline flow we have to discuss only, right? In streamline flow, as I told you, suppose this is the tube and the water is flowing like this, right? This is the water flowing like this, right? This is the steady flow. They move, right? They move in such a way that the velocity at a point is v1 when it reaches to the v2, as I told you. So the velocity does not change at a given point. Also, if the pressure is p1 and the pressure is p2, it remain always same. The density does not change. We will consider the incompressible fluid. The incompressible fluid mean, what is the mean of the incompressible fluid? Incompressible fluid. What is the meaning of incompressible fluid? Which cannot be compressed, whose volume cannot be changed. Therefore, density remains same at any point. Right? This is called the incompressible flow. And this is the streamline flow. What is the streamline flow? In steady flow, all the particles passing through the given point have the same path and a unique line of flow. Right? And suppose this is the line of flow. And this line of flow is called the streamline. This line of flow is called the streamline. The important thing is that the two streamlines cannot intersect. Two streamlines cannot intersect. If they do so, right, like this, so at the one point, there will be two velocities, which is not possible, because at a given point only the one velocity is possible. So therefore two streamline cannot intersect. If they do so, there will be two velocity at a single point, which is not possible in steady flow. Is it clear or not? In the streamline flow, we will discuss the streamline flow, the laminar flow. What is the laminar flow? You can read the definition. Particle move in the laminar flow with well-defined streamlines, right? And these streamlines are parallel and straight, right? For example, this streamline flow is what? The laminar flow. What is the laminar flow? The particle moves steadily, right, on, right, straight and parallel streamlines. Is it clear or not? In this flow, in the laminar flow, the velocity, right, may be different at different points, but at a given point, velocity of all particles are velocity is same, right? This is called the streamline flow. The other flow will be the turbulent flow, right? And I'm writing here only turbulent flow. What is the turbulent flow? In which the water molecule or the liquid, right, flow is zigzag, right? So we are not going to consider the turbulent flow. Only the laminar steady flow we are going to discuss, right? Copy this. Now, okay, so the equation of continuity. The next topic is equation of continuity. The equation of continuity is based on conservation of mass, right? Here we will assume the liquid is incompressible. What does it mean? Incompressible means which cannot be compressed. It means the volume remains constant, right? If the volume remains constant and the mass is always constant, so the density is also constant. Is it clear or not? That is the thing. So the equation of continuity, suppose this is the tube, right? This is the tube, you can consider, right, like this, and this is the big cross section, the area is A1. This is the small cross section, area is A2. Is it clear or not? Now, if the water is flowing in the streamline like this, right? This is the streamline flow. And the velocity at this point is what? Suppose the velocity is V1. Here, the velocity is V2. So, in delta time t, if it is moved by distance delta x1. So, in the same time, suppose this is the velocity delta V2 over here, and this mass come outside from the liquid, right? So delta x1 upon delta t is equal to what? V1, or you may write it is the dx1 upon dt, right? That is the thing. This is the limit delta t tending to 0, although this is the mathematical definition, you need not to worry about this, right? In the same way, what is the V2? Is equal to del dx2 upon dt. Is it clear or not? So the conservation of mass, in the same time, what the mass, therefore what the same volume, what the volume is going on, right, is entering in the tube, the same volume will come out from the tube, right? So the volume enter, or the mass, dm mass enter, must be equal to dm mass out. Is it clear or not? What is the mass? Say volume, small volume in, right? Or you may write volume in, volume out, into density, in the volume out into density. Density is constant. Why? Because the liquid is incompressible. What is the volume enter or in? Is equal to area A1 into, this is the elemental displacement. Volume out, the A2 into the dx2. If you divide by delta T, right, delta T. So now if you take the limit, it becomes dx1 upon dt, dx2 upon dt, then a1 dx1 upon dt is equal to a2 dx2 upon dt. This is a1 v1 is equal to a2 v2 is equal to constant. It means this is the equation of continuity. The velocity is inversely, it is equal to area multiplication of area and velocity is constant. It means velocity is inversely proportional to what? Say area. What does it mean? If the area is small, the velocity is less, velocity is more. You understand? So what does it mean? Suppose this is the tube, right, like this. So here the velocity is v2, v1, and here the area is small, the velocity is greater than v1. Is it clear or not? Practically you can see, if you take the water pipe, right, when you are spreading the water in the park or outside your house, right, or inside your house, with the help of the water pipe, when you press the mouth of the pipe, the speed of the flow, speed of the water flow increases or not? You tell. When you press the mouth of the pipe, the speed increases. Why? Because the area is reduced, therefore velocity is increased according to equation of continuity. Is it clear or not? You tell. Copy this. One thing, for example, I am giving you the application, right? Application of equation of continuity, right? First, the calm water is deep. Have you listened this thing? Calm water is deep, right? What does it mean? Tell me. Have you seen the flow of the river, right, and the flow of the canal? Suppose the river flow. Sometime the river may be deep, or sometime suppose this is the stone, right, the rock, and the water is flowing like this. Is it clear? So you tell, when the water is flowing like this, are you getting? So this is the horizontal level which will remain same, right? If this is the stone, suppose, right, or the rock, you can assume, right, here, right, you may assume this is the stone over here. So this is the height over here, and this is the height over here. Is it clear or not? You tell. This is the area of the cross section in which the water is flowing. The area of cross section is A1, and the flow of the water level over here is, suppose, the V1. But here the area of cross section is what? Say A2, the velocity is V2. Listen one thing. At the same time, the same volume has to pass from one point to another point. Is it clear or not? So that is why the velocity is less over here. It means it is very less. If this is the deep water, right, this is the deep water, the velocity is very less than as compared to this water. So when the water is deep, all right, and you will observe that it looks that water is still, it is not flowing. So you don't need to go in that type of the water which is at rest, which seem to be at rest. Because why it is rest? Because it may deep, very deep. Why? The velocity is very less, and this water looks still. Water looks like it is at rest because it is deep. And while the water depth is very less, so the velocity is very high. So if the water is flowing with the very high speed, so you may observe or you may conclude that the depth of the water is not very much high, very much deep. Is it clear or not? So that is the thing. So always remember, the calm water is always deep, and you need not to go in that type of the water. You understand or not? Tell me, have you listened this statement sometime? The calm water is rest, or calm water is deep, right? Copy this. So in this question we have the cylindrical tube, right, like a spray pump. right? In the spray pump, this is the piston, right, and it moves in this way, right? This is the piston, and the nozzle has a very fine holes. Suppose this is the very fine hole, right, like this, right? And the cylindrical pump has a cross section which has pump has cross section 40 fine hole area. The cross section of the spray pump, you may assume like this, right? Spray like this, A1 V1. So what is the area A1? The area A1 is 8 centimeter square, and here if this is the cross section, right, 8 centimeter square, there are small holes, very small holes. And how many holes are there? Say 40. And what is the area of the one hole? Is the area is A dash is 10 raised to a minus 8 centimeter square. Oh, meter square, sorry. It is meter square. Are you getting? So when the water or the liquid is flow, so the water will come out from this hole. Is it clear or not? So what they are asking by what speed the liquid will come out. If the speed is, in this case, what is the speed of this piston is given as, V1 is given as 0.15 meter per minute. So V1 is 0.15 meter per minute means 60 second, right? So this is 15 upon 600 meter per second, right? So this is 1 by 14, right? 1 upon 400 meter per second is the velocity of this piston. Is it clear or not? So how many holes are there? You will say it is 40. So I will apply the equation of continuity A1 V1. What is the volume per unit time it's going in this side, the same volume per unit time is coming out from the other side, V2. This V2 we have to find. The A1 is 8 centimeter square. The velocity is 1 upon 400. The area A2, this is in centimeter square. I will write into 10 ki power 4 minus 4 meter square. So it is better to write 8 into 10 ki power minus 4, right, in SI unit. The area A2, listen, what is the area A2? The area of the one hole is 10 to the minus 8. So how many holes are there? Say 40, right? And the area of the one hole is this and the V2. You are getting this thing or not? You tell me. Any confusion? Please tell. Now you can simplify this. The V2 is what? Is equal to, it is 2 into 10 ki power minus 6. When you will simplify, 4 to 8 minus 6, and this come in the denominator, minus 8. So this is 200 upon 40. So the answer is 5 meter per second. So from each hole, the liquid is coming out with the speed 5 meter per second, right? Copy this. So in this question, right, we have a syringe, right? The syringe, like we insert the injection, right, like that. So if this is the cross section, right, and the cross section of this piston is A, and we have a nozzle. The nozzle has a very small cross section, and this small cross section is small a. So when it moves with the speed V, so it comes with the speed V dash. So what is the V dash? So A1 V1 is equal to small a V dash. So what is the V dash? Say AV upon A. Now this is the height H. Are you getting or not? And the water perform the parabolic motion and it falls at this point. So this range we have to find. So this is the horizontal projectile, like horizontal projectile from the tower. So what is the time of flight? If you remember, the time of flight is 2 root h upon g. If you don't know, then I am explaining once again. The vertical direction velocity, initial vertical direction velocity is what? Uy is equal to 0, right? So in y direction, I will apply s is equal to ut plus half at square in y direction. The uy is 0, right? Vertical direction. What is the vertical displacement? Say h is equal to ay is what? G into t square. So h is equal to half gt square, t is equal to what? 2h upon g. So this is the time. So in x direction, what is the range? S is equal to ut plus half at square in x direction, right? In x direction, what is the acceleration? Say 0. In the x direction, what is the speed? The v dash, and the time is root 2h upon g, right? So the horizontal displacement is r. What is the v dash? Is a upon small a root 2h upon g. So this is the range of this system, right? Copy this. So now we start the Bernoulli theorem. In the previous lecture, we had discussed the equation of continuity, right? Now write the heading Bernoulli theorem, right? The Bernoulli theorem is based on, it is a theorem which is based on principle of conservation of energy, conservation of energy, conservation of mechanical energy, mechanical energy, right? Conservation of mechanical energy in fluid dynamics, right? In fluid dynamics. What is the principle of conservation of energy, right? First of all, the thing is that for the Bernoulli theorem, right, we will discuss the fluid is the non-viscous, right, incompressible, and the steady flow, that is the laminar flow we will discuss. All right. So there are three types of the energy we are going to discuss. First is the kinetic energy, right? Kinetic energy. Listen one thing. When, if this is the tube, right, and the fluid is in the steady flow or the laminar flow, you can say, right, like this. So if you consider the dm mass, right, it has the kinetic energy dk is equal to half dm into v square at some point. Is it clear or not? So the kinetic energy, this is the kinetic energy in joule. So the kinetic energy per unit volume, kinetic energy, kinetic energy per unit volume. What will you write? D half dm into v square into dv. What is the dv? dv is the volume. Suppose dv is the elemental volume, is equal to a into dv is equal to, okay, dm. The dm mass in terms of density is equal to volume into density. So if you write this half, right, dm is equal to dv into rho into v square, the elemental volume will cancel out. So half rho v square. So this is the kinetic energy per unit volume, and the unit of this will be joule per meter cube, right? This is half rho v square. So this is the kinetic energy, right? In the same way, second is the potential energy. Potential energy mean, if you assume this is the reference, right, if it is a reference, so what is the potential energy? The potential energy, right, the potential energy is equal to what? mgh, right? In place of m, I will write the dm, and the potential energy per unit volume, right, potential energy per unit volume is equal to divided by dv. Again, the dm mass, the elemental mass, may be written as volume into density. So volume into density gh upon dv. So this is the rho gh, right? This is the kinetic energy per unit volume. This is the potential energy per unit volume is equal to rho gh, right? So this is the one energy associated with this fluid in flowing fluid, and this is the potential energy due to the some height, right? Now this is some height. Now the third type of the energy is the pressure energy, pressure energy, right? the pressure energy. The pressure energy is because of the pressure. When the pressure is applied, right? So it will apply the force. What is the force? So pressure upon area. So pressure into force into area, right? So what is the elemental work done by this pressure? Is equal to force into displacement, right? The displacement is dx, suppose. So the force is, pressure is equal to force upon area. So the pressure is equal to force upon area, and the force is equal to pressure into area. Now it is correct. So this is pressure into area, this is the force, this is the elemental work done by the pressure, right? Force into displacement. Is it clear? So this work done per unit volume, right? This is the volume, is equal to what? Is equal to P into X, P into A into dx upon dV. So what is this elemental volume? The elemental volume is equal to area of cross section into dx. So it will cancel out. So this is the P for pressure only. So the pressure energy per unit volume is nothing but equal to the pressure at any point. This is the kinetic energy per unit volume. Rho g h is the potential energy per unit volume, and pressure is also doing the work because we have to apply the mechanical energy conservation, and this is the pressure work per unit volume is equal to pressure at that point, right? Copy this. So in the Bernoulli equation expression, Bernoulli's theorem, right? So according to Bernoulli's theorem, the sum of all these three energy remains constant when the fluid flows in a steady flow, right? So in case of steady flow, when the, I'm not writing the definition, rather I'm uh, explaining the steady flow of incompressible and non-viscous fluid through a non-uniform cross-section area of the tube. The sum of all the energies, which energies? The pressure energies per unit volume, kinetic energy per unit volume, and the potential energy per unit volume remain constant, right? And suppose at any point, suppose this is the Bernoulli tube, right? And suppose this is the reference, okay? And this is the area, suppose this is the area A1, right? At this side the pressure is P1, the velocity is V1, area is E2, the velocity is V2, and the pressure this side is P2. This is the height H1 of this point, the height is H2. All right, so this is the theorem, that is P plus half rho V square plus rho GH is equal to constant, right? So I will explain or I will prove this, right? It is very important. So as I told you, this is based on conservation of energy, conservation of energy, of mechanical energy, right? So what is the conservation of energy? The conservation of energy is the total work done is equal to change in kinetic energy. I will apply the work energy theorem. What is the work energy theorem? Total work is equal to K final minus K initial. Is it clear or not? So suppose this is the dm mass, right? This is the dx1 and this is distance is dx2, right? So in this case, the v1 velocity you will write dx1 upon dt, no doubt. The v2 velocity you will write dx2 upon dt. Is it clear or not? Also the equation of continuity you will apply. What is the equation of continuity? Equation of continuity is a1 v1 is equal to a2 v2, or you may write a dx1 upon dt is equal to a2 dx2 upon dt. You may write also like this. Is it clear or not? And the conservation of mass is what? What the mass of the water in unit time is entering from one side, the same mass is coming out from the other side. That is dm in is equal to dm out. You can also write this, right? Like this. dm in is what? Volume into density, right? The same thing you will get, volume into volume V1 into density, volume V2 into density. The same thing you will get from this equation also. What is the total work done? The total work done is the work done by this pressure, right, and the work done by gravity. Listen one thing. Tell me one thing. If this is the dm mass, right, and if the dm mass comes down by height h or distance h, what is the work done by gravity? You will say, if it is coming down, the work done by gravity is mgh, dmgh. But if the dm mass is taking upside, right, then the force dmg will act downward and the displacement is upward. So in this case, the dmg force is acting downward and the displacement is also in the downward direction. So therefore the work in this case is plus dmg, while you are taking this dm in the upside, right, against the gravity, then the work done by the gravity will be what? Minus dmgh. You understand this thing or not, you tell, right? So in the same way, you consider this side. If this is the dm mass which is moving up, by what distance it is moving? This distance is h2 minus h1. So what is the work done by gravity? Work done by gravity, right? Work done by gravity. What is the work done by gravity? Is equal to work done by gravity is equal to minus dmgh. What is the displacement? Say h2 minus h1. Is it clear or not? You tell. Listen one more thing. This is the work done by gravity, and now I will find the work done by pressure. Work done by pressure, right? Work done by pressure. How to do that? Listen one thing. If this is the pressure, at this point is pressure. So what is the F1? Say P1 pressure is equal to force upon area. The force is equal to P1 into A1. So in this side, the force F1 is acting and the displacement is in this direction. So here the work done by this side, by the pressure, is equal to F1 into dx1. Is it fine or not? And it will be positive. Why? Because force and the displacement both are in the same direction. But in this side, if this side the pressure is P2, right, and therefore the force F2 will be acting in this direction. Is it clear or not? Suppose the pressure is P2, the force acting in this direction, while the displacement dx2 is in this direction. So here the pressure work will be negative. How much it is? Minus F2 into dx2. Is it clear or not? Tell me. So this is the work done by gravity and this is the work done by pressure. Is it clear? So what is the work energy theorem? Total work is equal to change in kinetic energy. If we apply the total work means work done by gravity plus work done by pressure is equal to K final minus K initial. What is the K final, you tell? If this is the dm mass, this is also the dm mass. So its kinetic energy become half dm into v2 square. This is the final kinetic energy. And this is the half dm v1 square. This is the initial kinetic energy. Is it clear or not? You tell me, what is the work done by gravity? It is minus dmg h2 minus h1 plus what is the work done by pressure? This work minus this work, that is F1 dx1 minus F2 dx2, right? This is the work done by gravity, this is the work done by pressure, is equal to half dm v2 square minus v1 square. You may write, right, or simply write half. So what is the value of the F1? The F1 is P1 into A1, right? P1 into A1 dx1. The value of F2 is pressure into area A2 into dx2, right? And this is minus dmg h2 minus h1, right? This is as it is. Listen one more thing. Here, look, this is the A into dx1, A into dx2. So A1 dx1, A2 dx2. Is it clear or not? A1 dx1 is equal to A2 dx2. And listen, one more thing. Here I am writing. In the rough, you can write the dm mass is equal to volume into density. Volume is what? Say area into dx into rho. So you tell me A into dx. A into dx is equal to dm upon rho. Right. So the A1 dx1 is equal to A2 dx2. The A1 dx1 at this point, A2 dx2 are equal, and which is equal to what? Say dm upon rho. Dm upon rho. Is it clear or not? You may write over here in the rough or whatever you want, but A1 dx1 is equal to A2 dx2 is the elemental volume, right? You can say A1 dx1 is equal to A2 dx2 is what? Say elemental volume, and elemental volume is what? Elemental mass divided by density, right? So what the volume is entering at time, in any time t, the same volume is coming out. So A1 dx1 is equal to A2 d2, right? It is also come from the equation of continuity, right? So dm upon rho. So this is the P1. What is the A1 dx1 and A2 dx2? Both are equal, is equal to, you will write it is dm upon rho, right? And minus dmg h2 minus h1. This is dm into g, and this is equal to what? If you take half dm common, right? So is equal to v2 minus v1 whole square. Half dm v2 minus v1 whole square. This dm will cancel out, and this is the density rho. When you will multiply, so this is rho g h2 minus h1 plus p1 minus p2, and this density is also multiply this side. Fine. So if this is half rho v2 square minus half rho v1 square, and this is equal to what? Minus rho g h2 plus rho g h1 plus p1 minus p2, right? So now p1 plus half rho v1 plus rho g h1, p1 plus half rho v1 plus rho g h1 is equal to, this p2 goes right side, p2 plus half rho v2 square, right? Half rho v2 square. This goes to right side, rho g h2. So this is the expression for the Bernoulli equation, which is equal to constant at any point in this tube. So what is the Bernoulli equation? This is the proof of the Bernoulli equation, that the sum of the pressure energy per unit volume. This is the kinetic energy per unit volume. This is the potential energy per unit volume. When incompressible and non-viscous fluid flow in steady manner, right, the sum of all this energy remains constant, right? So this is the proof of the Bernoulli equation, right? Copy this. So I'm just revising this. What you have to do, you have to apply the conservation of mechanical energy. The total work is equal to change in kinetic energy. Here this is the dm mass, right? The velocity become v2, the velocity was v1. So the change in kinetic energy is this. And what is the total work done by the gravity? The gravity work done is minus dmgh, right? And what is the work done by pressure? The pressure, it is plus f1 into dx1. In this case, minus f2 into dx2, right? Because the displacement is, water is flowing in this way, fine, and the force is acting in this direction, right? And rest of the thing you know very well, right? So that is the thing. In this case, the special case may be there, right? And what is that? If the this, you may write like this. If you want to write this here, the pressure energy, right? The pressure energy per unit volume plus kinetic energy, I'm writing in short, pressure energy per unit volume, kinetic energy per unit volume, right? And this is the potential energy, right? This is the pressure energy per unit volume. This is the potential energy per unit volume remains constant. Is it clear or not? If the important thing is that if you give by the rho gh, if you divide every side is rho g, right? And this is the v square upon 2g. This is called the h. This is again the constant. This terminology or this expression or this term is called the pressure head, right? This is called pressure head, fine. And this is called the velocity head, right? Technically this is called, and this is called, this h is called the gravitational head, right? Gravitational head. So the sum of pressure head plus velocity head plus gravitational head is also constant. You may write in this way. This is the other way to write the Bernoulli equation. Is it clear or not? Where it will be used? It will be used in the horizontal tube. If Bernoulli tube, right, or is horizontal, if tube is horizontal, right, horizontal tube, you may write for horizontal tube. For the horizontal tube, the H1 and H2 both are equal, right? For example, suppose this is the tube, all right, and this is the horizontal. So at this point, suppose the velocity is V1, at this point the velocity is V2, the pressure is P1 and the pressure is what? Say P2. So the water will flow or the liquid will flow in this way. Are you getting or not? Right. So if you apply the Bernoulli equation at the 2 points, right, at this point and this point, suppose this is the point number 1 and this is the point 2, right? P1 plus half rho V1 square plus rho GH1 is equal to P2 plus half rho V2 square plus rho G H2. But H1 and H2 both are same. So the P1 plus half rho V1 square is equal to P2 plus half rho V2 square is equal to constant. It means the pressure head, you may also write the pressure head plus velocity head is equal to constant. So sum of pressure head plus velocity head is constant for horizontal tube. What does it mean? It means if the pressure is more or the pressure head is more, right, the velocity head will be less and vice versa. For example, if you consider this is the horizontal Bernoulli tube, this is the area A2, so the velocity will be more, and you tell me if this is the area A1, the velocity will be less according to equation of continuity. I think you understand this, right? So if the velocity head is more, the velocity head is more over here, and the pressure is P2 this side and the pressure is P1 this side. So what will be the relation between P1 and P2? Here the V2 is greater than V1. Why? Since A2 is less than A1, therefore V2 is greater than V1. It means at this point the velocity head is more. So pressure head, what is the relation between the pressure P1 and P2? Right. If V2 is greater, then pressure P2 this side will be less. So when the cross section become smaller of the tube, at that point the pressure become less, right? Copy this. Now we will see the application of Bernoulli equation. The application of Bernoulli theorem, right? Application of Bernoulli theorem. The first application is Venturi meter. Venturi meter is the device, right? Venturi meter or flow meter it is also called, and it is used to measure the flow of liquid, flow of liquid, right? For example, if in river the water is flowing, by what rate the volume flow rate is to be measured with the help of this Venturi meter, right? This device. Although this is of the two types, right? And the question are also asked on both. So I will solve the both Venturi meter. The first Venturi meter look like this. This is the big cross section. Then here the cross section become smaller, right? Like this. And this is the smaller cross section. A vertical tube is over there, right? This is the one of the Venturi meter. The two vertical tubes are there, all right? So this is the cross section area A1, you can consider. This is the cross section area A2, you can consider. Here the when, listen one thing, if in the river the water is flowing, so these are the two tubes, right? So by holding this, we dipped all this device in the flowing water. So what happened? The water will start flowing in this way, right? Like this, like this. Is it clear or not? It flows like this. Is it fine? Right? And what will happen? You tell. If the water start flowing over here, the velocity is v1, and at this point the velocity will be v2. Can you tell me which velocity will be greater? Here the A2 is less than A1. Therefore, velocity head at this point, or the velocity of the flowing liquid, will be more. Are you getting? Therefore, if you consider the pressure is P1 over here and the pressure is P2 over here, right? Since the velocities has it more, right? The velocity head is greater, so the pressure is less. So the water rise up to height h1, the less height. Here the pressure is what? V2 is greater, so the pressure is less. Therefore, the pressure P2 is less than as compared to P1, and the here pressure is more, so the water is filled, right, or liquid is rise to the more height. The difference in the height we can measure by the meter scale mounted at this side, right? This is the meter scale, like this. So by this meter scale, 0, 10, 20, 30, 40, right? We can measure the height in the measure the difference in the height of the water column in both right arms. Is it clear or not? So although this is a horizontal tube, so we can apply at point 1, at point 2. This is the point number 1, this is the point number 2. Apply Bernoulli equation, Bernoulli theorem at point 1 and at point 2. What is that? P1 plus half rho V1 square plus rho G H1 is equal to P2 plus half rho V2 square plus rho G H2. But H1 and H2, but tube is horizontal, you can say. So these terms are cancelled. Is it clear or not? And P1 is greater, so we can modify this. P1 minus P2, right? P2 goes this side, is equal to half rho V2 square V1 square. Half rho. You may write this the V2 square, 1 minus V1 square upon V2 square. Is it clear or not, you tell? What is the pressure difference at this point? Suppose this height is the H1 height, right? This height is H2 height. Are you getting or not? You may assume this is the H. So what is the difference in the H1 and H2? At this point, what is the pressure P1 you will write? This is open to atmosphere. This is open to atmosphere. At this point, the pressure P1 you will write P0 plus H1 rho G. Rho is the density of the water, it is, or density of liquid. And what about the pressure P2? The pressure P2 is P0 plus H2 rho G. Which pressure is greater? See, P1 is greater, right? So what is the difference? If you make the difference P1 minus P2, right? So it will cancel out and you will get is equal to H1 rho g minus H2 rho g. Inside you can write. So the pressure difference P1 minus P2, right? Here we can write H1 rho g minus H2 rho g. So rho g, if you take common, this is the H1 minus H2 is equal to half rho V2 square, right? This is H1 half rho V2 square. Now, one more thing. What is the relation between A1 V1 and A2 V2? Because we cannot measure the speed V1 and V2 inside the Venturi meter, but diameter of this thick tube and diameter of this thin tube, that is its area A1 and A2 we know. So we will apply A1 V1 is equal to A2 V2. So V1 upon V2 may be written as A2 upon A1. So here V1 upon V2 is replaced by A2 square upon A1 square. Is it clear or not? Copy this first of all. Any doubt you want to ask, Varsha? So rho GH, rho will cancel out, right? H2 minus H1, right? The H2 minus, sorry, H1 minus H2 is equal to what? H is equal to half V2 square is equal to 1 minus A2 minus A1 square, right? So this is multiplied. I think you understand this. So the V2 square is 2GH upon, right, A2 square upon A1 square. Is it clear or not? So if you take the square root, you will get 2GH upon, right, 1 minus A2 square upon A1 square. If you take multiply, if you multiply, take the LCM, multiply, and it goes in the numerator, the A1 square come outside. This is 2GH upon A1 square minus A2 square. So this is the velocity at this point. But I told you we cannot measure this velocity, and we are not going to measure this velocity V1 or V2. Although this is the velocity value, right? In some question they may ask the velocities like this. Is it clear or not? You tell, right? And if they ask what is the velocity V1, so how would you find the V1, right? So the V1 is nothing but A2 upon, the V1 is A2 upon A1 into V2. So A2 upon A1 into V2. What is the value of V2? This is the value of the V2, and A2 upon A1 root over 2GH upon A1 minus A2 square. So the A1 will cancel out. So V1 is equal to what? Say A2 root 2GH upon A1 square minus A2 square. So this is the velocity of the V1 and velocity of the V2, but our objective is not to find the velocities at this point. Are you getting or not? Our motive is to measure the flow of liquid. The rate of flow is measured to used to measure the rate of flow of liquid, right? Or it is better to write volume rate flow, right? Volume rate flow, right? Volume rate flow of liquid. What is the volume rate flow of liquid? Can you tell? The volume rate of flow of liquid mean per unit volume, per unit time, what volume is flowing through this, right, Venturi meter. And this is equal to what? Say A1 V1 is equal to what? Say A2 V2. This is the equation of continuity. Right? It may be written as dx1 upon dt, dx2 upon dt, and dt will cancel out. What does it mean? A1 dx1 is equal to A2 dx2. Is it fine or not? You tell. So this is the elemental volume V1 and V2, right? And the A1 V1, listen one thing, A1 V1 is equal to AB is equal to constant. What does it mean? A into dx upon dt is equal to constant. It means dv upon dt is equal to constant. So look, the a1 v1 is nothing but a1 v1 is nothing but, you may write like this, a into dx upon dt is equal to dv upon dt, right? It is better to write in this way. The equation of continuity is a1 v1 is equal to a2 v2, that is multiplication of area and the velocity at any point is constant, is equal to a into dx upon dt, dv upon dt. This is called volume rate flow. It is very important line, right? What is the volume rate flow? That is the volume rate flow, either you can write a1 v1 or you can write a2 v2, and this volume rate flow we have to find, right? We have to find volume rate flow of the liquid. So if you take the v1 value, so a1 into a2 root over 2gh, a1 square minus a2 square. So this is also equal to the volume rate flow. If you take a2 v2, it will also come equal. It is equal to a2 into v2, right? If this is v2, multiply by a2, what will you get? a1 a2, right? When v2 is multiply a1, here the same thing you will get 2gh upon a1 square minus a2 square. So this is the volume rate flow. This is the volume rate flow. So volume rate flow is measured by, listen, a1 and a2. a1 and a2 are the cross section of this Venturi meter, which is already known, right? And by measuring this height h, that is the difference in the two arms of the liquid rise, if you are able to measure, then you can write the value of dv upon dt. Is it clear or not? Varsha, copy this. So it was the very first type of the Venturi meter. The other type of the Venturi meter looks like this. It is a thick cross section. Now it is the thin cross section, right? Instead of the two vertical upside arms, right, there are the U-tube, and these are the two arms connected in this way, right? Like this, and here the, if this is the cross section area A1, this is the cross section area A2, this is the A1, this is the A2, and listen one thing, here the different immiscible liquid is filled in this arm already, and this is the density we can assume to be rho m. Is it clear? Whenever you need to measure the rate of flow of the liquid, this is dipped completely. So when the water start flowing like this, right, like this, when the water start flowing in this way, all right, like this, so because of this thin cross section, the velocity is more, and at this point the velocity is less. Fine, therefore the pressure is more, right, and the pressure at this point is less. Is it clear or not? If the pressure is less, if this pressure is less, this liquid move upside little bit and this liquid move downside. So initially both are in the same level, but when the fluid start flowing, due to the pressure difference, there is the difference in the height of the liquid, and whose density is rho m. Is it clear? The density of the fluid here you can assume to be rho. Is it clear or not? If this is the point 1 and this is the point 2, we can measure this height h, right? If you consider the pressure P at this point, right, at this point, so what is the pressure difference? First of all, you tell, right? You can assume the pressure at this is P1, if this height is h1 and this height is h2. Is it clear or not, you tell? So the pressure at this point will be the same. At this point, what will be the pressure? P dash, P1 dash. At this point, the P2 dash. The P1 dash will be equal to what? P1 dash is equal to what? Or instead of this, you may write in this way. If the pressure at this point is P1, P, and the pressure is P also. So when you move up, the pressure will decrease or increase. Suppose the water is also filled over here, right? So what is the pressure? If this is P, if you move up, the pressure will decrease or increase. The pressure will decrease by what amount? P minus rho GH, right? P minus rho GH1. So this is the P1. At this point, if this is the pressure, this is the density of the liquid, rho m, right? This is the rho, this is the rho. So what will you write? The pressure, wait for 1 minute. This is the pressure P1. What is the pressure P2? The P2 is P minus H rho m into G minus, this is the liquid density, right? This is H rho 2, right? You can write P1 minus P2, right? This is the rho m, or you may assume this is the air over here. So this is the liquid pressure is, you may assume this is rho H1 rho mg, because all over air is liquid, right? This is the H2. So the P1 minus P2 is equal to what? H1 minus H2 rho medium into G, right? So the pressure difference P1 minus P2, the H1 minus H2 will be equal to H rho medium into G. So this is the pressure difference. Listen one thing, I am not taking this liquid into calculation. The pressure difference is only because all over here the pressure, the liquid is only there, right? And nothing is present at this point, right? Here it is the air, or you can say it is water. So the pressure difference between P1 and P2 can be calculated by this height difference. So P1 minus P2 is equal to H rho m into G. It should be clear. Is it clear or not, you tell? Yes, very good. So listen one thing, need not to be confused with this height H1 and H2, right? So the pressure P1 and P2 if are there, the P1 is greater, P2 is less, and the difference between P1 and minus P2 is due to this liquid column, right? Now we can apply the Bernoulli equation at this point, the point 1 and point 2, right? Apply Bernoulli theorem at 1 and 2, and this is the horizontal tube. Is it clear? So P1 plus half rho V1 square is equal to P2 plus half rho V2 square. It is horizontal, so H1 and H2. What is the rho? Rho is the density of the liquid flowing in this Bernoulli tube. So the P1 minus P2 is equal to half rho V1 minus V2 square. So P1 minus P2 is nothing but H rho m into G is equal to half rho. This rho is different from this H, this rho m. And if you take the V1 square common, V2 square minus V1 square now. And the V2 upon V1 is nothing but A1 upon A2. So this 2G rho m, right? 2H rho mg is equal to V1 square. Fine. This is the density rho. 1 minus A1 square minus, wait for 1 minute, there is some mistake. This is V2 minus V1. If you take V2 square common, this is V1 upon V2. So the V1 upon V2 may be written as the A2 upon A1. So this is A2 square upon A1 square. So what is the V1 square? You will write 2GH rho m upon rho 1 minus A2 square A1 square. So what is the velocity V1? This is 2GH rho m upon rho into 1 minus A2 square upon A1 square. Fine. Again, we need not to find the speed V1 or V2. Although the V2 can be found with the help of the A1 upon A2 into V1. but we have to find the rate of flow, right? Volume rate flow, that is equal to A1 V1 is equal to A2 V2. So if you simplify it further, so it may be written as A1 2GH rho m. Rho m is the liquid density filled in this U tube, and this is rho A1 square minus A2 square. If you multiply by, wait for 1 minute, this is equal to V2, this is equal to V2, this is equal to V2, right? So to find the volume rate flow, this is A2 V2, multiply by A2 now, so A1 A2 root over 2GH rho m, and this is rho A1 square minus A2 square. So this is only the little difference. This is the volume per unit time in meter cube per unit time is equal to A1 A2 root over 2GH rho m rho A1 square minus A2 square. Is it clear or not? The unit I am writing, this is in meter cube per second, right? So the second application of Bernoulli equation or Bernoulli theorem is Torricelli law, right? Torricelli's right law and of efflux, right? Torricelli's law or speed of efflux. What is that? I'm telling you. Suppose if this is the tank, right, and the tank is full with water, right, and you make a little small hole over here, so then what will happen? Suppose the height h of the water or the liquid fluid flow filled in is the h. When you make the small hole, suppose the area is a, this is the big cross section, and the small hole if you make of the cross section area a, what will happen? The water will flow. So this speed you have to find, right? So this speed can also be found with the help of what? The Bernoulli equation. Suppose this is the point 1 and this is the point 2 you can consider. So when the water is flowing, the level liquid will come down. Suppose at this point the speed by which this layer is coming down is the V2 and this speed is V1, right? So equation of continuity. What is equation of continuity? You tell. A1 small a into V1 capital A into V2. This is the one equation. All right. If it is open to air, so at this point the pressure is atmospheric pressure and the water is also coming into the air. So at this point the pressure, right, is also equal to the atmospheric pressure. But sometime this pressure is not the atmospheric pressure. In some example I will give you that illustration also. But here the P1 and P2 are same. So you can, if you assume it is the reference, you can apply the Bernoulli equation, right? Bernoulli theorem at point 1 like this and at point 2. What is that? P1 plus half rho V1 square plus rho G H1. P2 plus half rho V2 square plus rho G H2. So what is the P1 at this point? Say P0 plus half rho V1 square, right? And what is the H1 over here? Say 0. And what is the H2 over here? This is the H2 is equal to H plus 0. The pressure is P0 half rho V2 square rho GH. And I think P0 you are getting this thing, right? So the rho will also cancel out, right? This is the rho. So V1 square upon 2 GH, right? The H. So if you simplify this, V1 square minus V2 square is equal to 2GH. Is it clear? So if you take V1 square common, 1 minus V2 square upon V1 square is equal to 2GH. So the V1 square is equal to 2GH upon V2 minus V1 whole square. And if you apply the equation of continuity, V1 upon V1 is equal to what? small a upon capital A. So V1 square is equal to 2gh square root, I am writing a upon a whole square. So V1 is equal to, so this is the speed of the efflux, right, by which the water is coming out. But important thing is that if you make a very small pinhole in the big tank, so the small area A is very less than A. So A upon A, approximately it is 0. So V1 is equal to what? Root 2gh. So this is the speed of a flux. What does it mean? What does it mean? It means if this is the initial velocity 0, so after falling height h, what is the speed? Say root 2gh. So it acts, the fluid acts like a freely falling body, right? So therefore the speed of this water flow at this point will be root 2gh. Is it clear or not? Although this is the derivation, but you have to remember the result. Is it clear or not? Copy this.